Welcome back. In this video, we're going to look at how we solve systems using a second technique, the method of substitution. It says here it's best to use substitution to solve systems when one of the equations is already solved for one of the variables, or if it can be easily solved for one of the variables. So if we have like one of the equations is y equals 5x minus 6, that equation's already solved for y, that's a good opportunity for us to use substitution. Or if we have an equation that we can really easily solve for one of the variables, say we have something like 2x plus y equals 5, it's really easy to just subtract 2x from both sides and get y by itself. Those are the optimal times to use substitution. In order to use substitution, we're going to follow these steps. We're going to solve one equation for one variable. Sometimes that'll already be done. If it's not, that's what we need to do first. Then we're going to substitute the value of that variable into the other equation. And when we do that, it should leave us with an equation that contains only one variable in it, which will enable us to solve for that variable. And that's what we're going to do next. We're going to solve that equation for the remaining variable. Once we find the value of that, we're going to substitute that value into the equation that we had in step 1 in order to solve for the value of the other variable. Once we have those two values, we're going to write our solution as an ordered pair, and we're going to check our answer. So let's go ahead and look at a few examples. We're going to first solve this equation using substitution. Y equals 2x minus 5, and 3x minus 2y equals 4. Notice we already have one equation solved for y. Y is equal to 2x minus 5. And so what we're going to do is we're going to take the y in the other equation and replace it with 2x minus 5. Now everything else in that equation stays the same. So we still have a 3x, we have the minus 2, and we're going to put that 2x minus 5 inside parentheses to remind us that that whole thing is y, because we want to make sure we distribute that minus 2 through the parentheses. And now that leaves us with an equation that has only one variable, x, and we're going to solve this equation for x. So we've got 3x minus 4x plus 10 is 4. Combine our x's. It's negative x plus 10 equals 4. Subtract 10 from both sides and divide both sides by negative 1. We get x equals 6. Now we're going to take that value and we're going to substitute it back into the already solved equation in place of x in order to find the value of y. Put that 6 in there for x and do our calculations. And we end up with y equals 7. Now we're going to write our solution as an ordered pair. X comes first, so that's 6 comma 7 is our ordered pair. And we're going to check and make sure that value works in the equation. So let's see, I put 6 in for x in the first equation. It better work here because that's where we got the x value from, or the y value from to begin with. So when x is 6, y is 7. And then we'll put it into the other one. 3 times 6 minus 2 times 7. And this better equal 4. And it does. And so our solution is good. All right. Next example. All right, in this system, we don't have an equation already solved for one of the variables, but we do have an equation that will be very easy to solve for one of the variables. In fact, we have one that is pretty easy to solve for either x or y. That equation, x plus y equals 3, I can either solve for x or y very easily, and it's really a matter of personal choice or just random chance. Since I can solve it for either x or y, it doesn't matter which one I solve it for. I think I'm going to solve it for x. So I subtract y from both sides, and x is equal to negative y plus 3. And now, since x is equal to negative y plus 3, I'm going to replace the x in the other equation with negative y plus 3. So I've got 4 times negative y plus 3 plus 3y equals 14. And now I'm going to solve for the variable that remains. We still have a y in the equation. We distribute the 4. Combine like terms. Subtract 12 from each side. Divide both sides by -1. We get y equals -2. Now I'm going to take that and put it back in here to find x. So x equals the opposite of -2 plus 3. That's 2 plus 3. So x is 5. So our ordered pair is 5, -2. And now I want to check that. And so I've got 5 plus -2 should equal 3 in the first equation. And 4 times 5 plus 3 times -2 should equal 14. And it does. And so our solution checks. And that is our solution to this system of equations. All right, one more. I'm going to solve this one using substitution. Notice the first equation is already solved for y, so I'm just going to take what y is equal to, and I'm going to put it into the other equation in place of y. We've got 4x plus 2 times -2x plus 7 equals 19. And I distribute my 2 through. And I combine my like terms. Whoa, all the x's disappeared. And sometimes this happens to us when we're solving systems algebraically, and we need to understand how to interpret this. Sometimes when we make a substitution like this, we end up with a scenario where all of the x values or all of the y values disappear and we're just left with numbers. This tells us that our system is one of two scenarios. It is either a system where there are no solutions, or it is a system where there are infinitely many solutions. And that depends on the truth value of this statement that we get right here. If it's true, that means there are infinitely many solutions. If it's false, that means that there are no solutions. So, is the statement 14 equals 19 true or false? Hopefully you're screaming out, false, it's false, Mr. Thomas, it's false. And yes, it is false. And so that tells us that this system has no solutions. All right? And that's how we see the special cases. If you remember the last example from when we did our graphing, little graphing lesson on systems, this is the algebraic situation that ties to, two parallel lines where they don't intersect. And there's no solutions. This is the algebraic equivalent of that scenario. All right? Okay. Next video, one more method for solving systems. See you next time.